So this is what we're going to make. One of my students slash mentees asked, how can I constrain a particle system to inside a mesh or a volume? And so I thought it was a fun exercise to try and tackle using POPs. The model on the right here is what's being loaded. And this is actually an animated FBX, but I've just frozen it for the time being. And that's just a normal, triangular mesh. And then the stuff on the left here that you're seeing is the particle system that's being created inside this model. It's one thing to do this if it's static, so I'm going to cover that. And then if this model actually starts animating, and let's bring that to life. So yeah, there's that model running, and here all these particles are being created inside. Yeah, so this is what we're going to make using POPs. Okay, so let's get on with it. So here we are in Touchdesigner. I'm using the experimental version 2025 3960. This was just released. Let's bring in a model first. And I'm going to bring in an FBX comp. And let's open up this humanoid and import that. And there we have this running figure. And I'm going to cheat, not do this properly. I'm just going to do, oops, not import. I'm going to do a select, because this is a whole comp. And if you go inside, there's a whole bunch of stuff here. And there's this humanoid. I just want to get this pop. And that's called deform inside FBX1 humanoid. So I'm just going to copy that. Go back up here, and I'm going to write it here. So FBX1/humanoid/deform. So there's my model. And let's split my view into two, make that a geometry viewer. Now I want to start with a stationary model. That's going to be a lot easier. So I'm going to go here, back to my FBX, go to the play and just do specify index. And here on the index, let's just choose a nice frame. Yeah, that's a good one. Okay, I don't want to display or render that, by the way. Let's add a null straight away. And let's call this null model. This is what we're going to reference from now on if we need to show anything. One thing we can do, there it is. Let's H that. So let's say we want to create a whole bunch of particles inside this. We can add a sprinkle. Sprinkle, and let's visualize that. Sprinkle by default sprinkles onto the mesh, onto the surface, but there is a method to sprinkle inside. This only works if the mesh is what's known as watertight, so that it doesn't have any holes in it. And there's no overlapping creases or things like that. So we've sprinkled some points there, and let's make that add some dynamism. Let's say we want to make those particles kind of wobble around, move around, etc. Can, for example, if we add a noise, let's visualize that. We add a noise, let's make the amplitude really big. See, it's this. If I disable, this is the original. This is with the noise. It's adding a bit of noise to the positions, but it's only doing this once. If we want to do this across time, we need to use the feedback top, because otherwise this whole graph is being executed every frame. It selects the mesh, sprinkles particles, add some noise, and that's what we see. But we want to accumulate this. If we want to accumulate this, we need to use the feedback top. So first things first, I'm going to save in case it crashes. Let's add a null. Let's add a null at the very end. This is going to be our very ultimate output. Let's visualize that instead of this. Then we're going to add a feedback top. And I like to kind of put it down a bit like indenting a block of code in text-based code. So I kind of indent my nodes. Let's add another null, which is the end of the loop. And I'm going to call that null end loop. And then we drag and drop that onto the feedback. And you can see immediately it's wiggling about, because now here we've created a closed loop. This bit here isn't running anymore. It just ran at the beginning. This ran, went into the feedback, and now you can see that we have a loop here. And that's going on forever. How do we constrain this to inside the mesh? Well, one thing we can do is if the particle leaves the body, we can reset it and put it somewhere back inside the mesh. So let's do this. After the noise, let's add, first of all, that noise is a bit too big. Let's bring that noise amplitude down a little bit like that. And the other thing is, this is fixed in time, so that's why it's stuck. So we'll do the kind of classic. I know some people don't like this. Let's just set apt time dot seconds. Okay. Let's slow that down a bit, divided by 10. And then bring this back down. Okay. Let's add an operator here, ray. And what ray does, it casts a ray from every point in the first input to the second input, see the collision geometry, so that we give it a collision geometry and a set of points, and it casts a ray from every one of these points here and to see where it collides here. And then it can give us a bunch of useful information as to where it hits and whether it's inside or not. This is the bit that we're going to need. So first of all, let's take this null model. And instead of dragging it all the way across like that, which we could do, I'm going to just add a select here just to keep my network tidy. I'm going to put my null model there, and I'm going to use that. So now every point here is casting a ray into this model, and I want to say, give me whether it's inside or not. So now every point here has a new attribute called ray inside. And in fact, I can do this. I'm going to convert that to a pop, to a dat. Let's open that. And you can see now, so every row is a point, the XYZ position, the normal, the noise that we said, and then a ray inside, whether it's inside or not. This is, as I said in previous videos, a bit slow, so I'm going to get rid of that. I don't want it. So now we have a ray inside, and we can do, well, one thing we can do, let's do a delete, for example. We can say attribute if ray inside is equal to 0, which means if it's outside, delete it. And as you can see, it's gone. But we don't want to do a delete. We want to do a math combine, our favorite. And let's reset this, go back to feedback and init and start. So far, we're not doing anything. We're wiggling all the particles around. Every particle has an attribute, which is whether it's inside or not. And now here, we want to do something if it's inside, and we want to do another thing if it's outside. So we can do this, A if C else B. A if C else B. We've used this before. C is a condition. So here, let's say ray inside. That's the condition. If the ray is inside, and we want to write to P, let's write P to P. So if it's inside, use the normal position. So that's A. Here we want to put something else. So if it's not inside, if it's gone outside, we want to use something else. So what can we use? Well, why don't we do this? Before we go into the feedback, after we've sprinkled, I'm going to create here an attribute. So this will only work for a static model. I'm going to change this later for a dynamic model, but this is the easiest thing to do. In attribute, we're going to create a new attribute. Go to duplicate. We want to duplicate P. Let's give it a new name. Let's call it home pos, the home position, or let's actually call it start pos. So we're creating a copy of its position. And you can see here it says start pos, which means we have a new attribute called start pos, which is basically, let's visualize this and don't visualize that. This is where we are at this stage. I'm visualizing this. We have duplicated that position attribute to start pos, and I can again convert that to a pop. And let's visualize it. There's P, position, the normal, and then start pos, which is identical to P. Then let's go here. I'm going to, instead of doing init start every time, because remember, once we're in this loop, we're in this loop. This stuff isn't being called. Like if I look at this position, in fact, you can just middle click. If I middle click on that, you can see that there's a start pos attribute. But here, inside this loop, there is no start pos attribute because we're already in the loop. We need to reinitialize this loop. Ignore that error. That error is there because I haven't put anything there yet. Let's just bypass that. So we need to re-init and start this. Now we have a start pos. So I'm going to just quickly add a keyboard in chop and then put that on the initialize and the start so that I can just press the one key to reinitialize my, every time I want to reinitialize this feedback loop. And let's get rid of that. So now inside my loop, every point has a start pos. So here on my math combine, I can say start pos. So if ray inside, use P. Otherwise, if outside, use start pos and write that to P. I'm going to put that up there. So this is like me indenting my code. That's my loop. And now let's run this. And okay, so what did I break? Oh, okay, I'm stupid. This is what we're displaying. So uncheck that and let's put this back on. Okay, here we go. So my particles are being created. They're wiggling around a bit. As soon as they go outside, they are being reset. There is one thing I forgot to do, and that's very important. I'm going to undo this just for a second. This ray, in fact, let's just visualize. I'm going to get rid of this noise. I'm going to disable all of these and restart. Okay, so now we're doing nothing because I want to talk a little bit about what the ray is doing. So select the mesh, sprinkle some points on it, copy. In fact, I'll rename this. I like renaming my nodes. Let's call that start pos. So what the ray, as soon as I enable this, so remember that we're sprinkling inside, so there's points all over. As soon as I bypass this, look what happens. Boom. All the points exploded and projected onto the mesh. The reason is this scale parameter. It's not updating as I change it correctly because the feedback is on. Let me get rid of the feedback. Okay, so now you can see what scale does. If scale is 1, it moves the point onto the surface where it's collided. So this can be very useful. Again, it's taking the incoming points, which are all these random sprinkled points, and then it's casting a ray from that point onto this collision mesh. And if scale is 1, it sticks it to the surface. We don't want to move them. Actually, we want them to be where they are, but we just want to have this ray inside. So now let's put these things back on. So there all my points are wiggling. As soon as I unbypass this, what's happening is the particles are jiggling around. As soon as they leave the confines of this collision mesh, they are respawned back to start position. So far so good. One little thing we can do is we are sprinkling points inside this mesh. Some of those might be very, very close to the surface. So one little trick we can do, let's have a look at that. That's our mesh. I'm going to come out here to another null, and let's call this sprinkle mesh. And let's visualize that. So that's our mesh. What we can do is add a math. This is a very, very naive way of doing what I'm about to do. I want to shrink this mesh a bit. And by shrink, actually, before, you might think, let's just do a transform. That's what shrinking is, right? Let's just take the scale down. But no, that's not what we want to do. We want to shrink it inwards. So a nice way, well, a very, very easy way to do that is to take the normal. Normals are vectors that point perpendicular to the surface. They point outwards. And they're used for lighting calculations and things like that generally. But another thing we can do is I can add a math combine here and say A plus B times C. We're going to take the position and write the position. We want to take the normal, multiply it by something, let's say 1, and add. So in this case, it got really fat. So this is the original mesh. Let's add the normal times 0.1. You can see it's getting a little bit fatter. We're pushing all the points outwards in the direction of the normal. We can also do that inwards. So if I do minus 0.1, see it's getting thinner. This is without that. This is the original mesh. And this is, whoops, this is just making it a little bit smaller. This is a little bit problematic actually, because if I do it too much, then it's going to stop being watertight. I also want to actually try something. I want to see if the normals are good. I want to recalculate the normals. Okay, yeah, look. So the original normals of the mesh look very problematic. Like this shouldn't be happening. So for some reason, the normals that are saved with the FBX are very noisy. So I'm going to use this normal node to recalculate the normals, and they're a lot smoother. So now I can make it a little bit smaller, thinner. But this does come at the risk of, in places like the fingers, it's collapsing on itself. There are ways of doing this shrinking using kind of more sophisticated methods, but I'm not going to go into that now. I'll just do this. So now I want to use this for my sprinkle. This way, I'm sprinkling points. Let's turn that off. I'm sprinkling points. It's guaranteed to be a little bit more inside the mesh. Makes the particles live a little bit longer, I guess. Okay, back to what we were doing. Turn that off, turn this on. Again, just to repeat what we're doing, we load the model, narrowed it down a little bit, sprinkle some random points, save the starting position, and then we go into our feedback loop. I'll just reset the feedback loop. Wiggle the position a little bit, cast the ray. The ray looks if it's inside this or not. If it is inside, carry on as normal, otherwise reset to the start position, and then we end the loop. And then we display. I want to call this math inside, so it checks if it's inside or not. And then outside of the loop, it's important to do this outside because we don't want to accumulate this. We can do, for example, trail. So one thing we can see is these lines. What's happening there is the point is wiggling around and then it's being reset. And because it's reset, it's drawing that big, massive line back to its start position. Oh, by the way, trail just basically leaves a history trail. That's quite straightforward. I'm not sure of an easy way using the trail node to get around this. If I were writing this trail node from scratch, or if one were doing that, which one could with a GLSL shader, one could put, for example, a distance threshold parameter, which in this case, we don't have here. But what we can do is instead of connectivity rows, we can just say point primitive. So it doesn't actually connect them. As you can see, if we say connected, it creates edges between the adjacent points. Let's just say point primitive. So it still keeps a trail, but it doesn't connect them with edges. And then we can instead use a proximity node. And then this connects edges that are connects points that are close to each other. To say, make that maximum 1 or 2 lines per point. And this creates kind of an interesting aesthetic as well. So the points are being created inside the mesh because of the sprinkle. Then they're wobbling around. They leave the mesh. If they leave the mesh, the ray checks if they're inside the mesh or not, and then the math inside checks if they leave the mesh. If they leave the mesh, it resets back to its starting position. Another nice thing about the trail is you can tell it to keep track of age. So let's say the age attribute, let's keep track of it. So I'm just going to disable the proximity just to make things easier to track. What this does is now it's keeping a history of all the points, but every point is also being aged. So new points have an age of 0, and then they get older and older up to, say, a trail length of, say, 2 seconds. Let's put the proximity back on. So we can do things now with this age attribute. Just to, let me save, again, do that to, sorry, pop to that. This might be a bit slow. Before I do that, actually, let me check how many points do I have. Okay, I have 1,000,000 points. No, I have a lot of points. If I try to visualize all of them as a DAT, it's, it could grind my computer to a halt. So instead of doing this like I was doing before and immediately converting it to a DAT, I'm going to cancel that. I'm going to create a pop to DAT. And it's got nothing in it. And I'm going to immediately just put thin random. So I'm going to say like really high. So this means thin out 95%. So only give me 5% of the points. Because I don't want to be pulling back 1,000,000 points from the GPU into a DAT. That's going to be super slow and it might crash my computer. I don't know. So now I can put this there. Okay, and now let's view this. This is only 5% of my points. It's enough to get an idea. You can see that there's my position. Every particle has a position, an age, which is from 0 to 2. In fact, we can get more than that. Let's thin. Okay, so we're getting about 20%. Yeah, you can see the full spectrum now. It's the normal, the noise. whether it's inside or not, etc. Okay. I'm going to just disable that. I'm going to keep it, but disable it in case I need it later. So every point has an age attribute, and we can do cool things with it. For example, let's set a size. Before I do that, let me set up a renderer. Let's create I want to instance a whole bunch of spheres onto this, so onto these points. So sphere, put a geocomp, and then we want a light. We want a render top, and we want a camera. I'm going to use this because it's easier to navigate. So here's my basic render. Why is that giving a no? What did I forget? No camera. Oh yeah. So there we go. And then let's enable instancing. Let's make that sphere 3. Let's make it tiny to begin with. Get rid of that and that's on. Cool. Instancing, let's put, I like calling these null points. So this is just point data at this point. Actually, I want to take that out and do this. So this, which is what was creating the edges, the triangulation, I don't want that there. This is just the raw point data. That's what I want to instance on. Turn that off, that's on. Put null points there. Oh, another thing I should mention, my frame rate is really low. One thing that's happening is every single pop, as you can see here, has its own renderer. It's best to just select everything, disable the viewer, and every new pop that you create, it's on by default. So if I insert something here, like, I don't know, a transform, it's on by default. So you have to turn it off. Maybe there's an option somewhere to have it off by default. But yeah, when working with pops, remember to turn off the viewers. It has a huge impact on the frame rate. Anyway, here we are back, null points and translate X. Let's do, yeah, there we go. If we want the size to be dependent on age, so when they're born, they're big, and then the trail gradually fades out. So what we can do is the trail gives the age attribute, as we saw. Well, that one can be on actually. You know, we have an age attribute. An age attribute is which is in seconds, so it's from 0 to trail length, which is 2. So the first thing I want to do, add a math combine, and do A divided by B. And we take age, we divide it by this number, paste that there, and then let's save that to age norm. So this is a normalized age. It's between 0 and 1. No matter how long they live for, even if they live for 5 seconds, age norm is a new attribute that's between 0 and 1. Now we can see that's on, the view is active, by the way. So I have to turn that off if I want to maintain it. Now what I want to do is I want to do a mix. And what mix does, it does linear interpolation. It does a kind of map. It's similar to in the math chop. You have this range, you map. Here you can map from a range to a range. It's similar to that, but it's always 0 to 1. So if you said, for example, mix from 1 to 2, and you said 0.5, it would be halfway between 1 and 2, it would be 1.5. If you said, let's say, from 10 to 20, by 25, that means 25% from 10 to 20. So in our case, we want to use age norm. We want to write to a new attribute called scale. And let's say when age norm is 0, so it's just been born, we want the size to be 1. When age norm is 1, we want the size to be 0. So it's shrinking. And I've just written that to scale. Let's visualize that. We're not using it yet. That's why they're all the same size. Let's go to geo, and in scale up is blank because we're still using null points. But we use here, let's just use scale. So now the particles, there's maybe too many particles, it's hard to see. Let's go back, go to the sprinkle. Oh yeah, 10,000 points. Let's make it 100 points just to see for now. See, I'm going to make it 100, nothing's going to change. Why? Because that's before the feedback. We're currently still in the feedback loop. In fact, let me indent it like this. That's easier to see maybe. And select that whole, and let's just select everything. Move it down a bit so that it's not aligned. Okay. I just wanted this line to not be overlapping with that line so you can see it easier. So I made that sprinkle 100 and we're not seeing any change because we're already in this loop. So I need to press 1 and to activate. That one can move on. Boom. And now I've reset. And so now we can see the effect coming into effect. So now there's only 100 particles. You can see they start big and they're gradually getting smaller. Let's make it 1,000 and reset. That's maybe too big. I can change that either via this. I'm going to call this map scale. I can either make this one smaller, or I can just change it here via this sphere. I can just change the sphere, which that's how I'm going to do it. So here's a bug I keep encountering. This is an experimental version. My geometry viewer is not responding to, I don't know why, but I have to close it. And I need to reopen it and then press H. Okay, now it's working. Okay, that's how we would do scale. What if we want to change the color? Like we want the new particles to have a different color. We want the particles to change color as they age. So we can do the same thing. We can use a mix. We can say mix. And we can say use age norm. And we can write to color. And we can say go from one color to another color. For example, 1 to 0. So when age norm is 0, it's just been born. It's the new ones, use it white. As it gets older, use black. And let's go to geo. We need to go to the second tab. That's where color is. And let's say use color 0, color 1, color 2. So that's RGB. And color 3 is the alpha, if we wanted to use alpha. So this, now the new ones are white, and as they get older, they go in black. What if we want more complicated, more complex mapping of color? So we actually have a lot of, we can do really interesting things. We could also do the same thing for scale, because this is a linear. What if we don't want it to just go 1 to 0, but we want it to follow a complex curve? So let's do that with color. I just undid that. Now this is giving a warning because we deleted the color attribute. There is no color attribute because I just deleted it. It was undo. There it was, but I'm going to delete it. No more color attribute gives an error. So this is what we're going to do. Let's move that over and let's go to ramp, color ramp. And let's say I want to use this as a lookup for the age. So when it's newly born, so age is 0, I want it to be whatever is here. Let's say I want it to be white, and let's flip it around. So when it's newly born, I want it to be white. And then as it gets older, it goes across. And then, when it dies, when the trail dies, it's black. And in between here, for example, I want it to be kind of like a lightish green, cyan rather. And then as it gets older, it gets kind of a bit more bluish, like something like that. So let's use this as a lookup. This is the top, it's a texture. I want to use it as a lookup. So lookup texture. There we go. Again, I added a new pop and it's got a viewer, which is going to slow things down. I have to disable that. Remember to do that. So in the lookup tech, let's call this, in fact, I'm going to add a null in case I want to insert something. Null, and let's call this age color. Or in fact, let's do it the other way around. Color by age. Put that here in the top field. What attribute do we want to use to look up into this texture? U is horizontal, V is vertical, W is depth, if it was a 3D texture. I covered this in a previous tutorial to do with the text particles. This is not a 3D texture. We can ignore W. We don't want anything vertical to look up, so we don't need that. Horizontally, we want to use age norm. So now we are using the age norm attribute, which is from 0 to 1, to look up here along the U axis, which is horizontal. And we still have a warning because we are looking this up, we're getting a value. There's a few other details here that we can ignore for now, which is lookup index units, they're normalized. Yep, we are sending normalized and we're looking into this in a normalized fashion, so that's all good. We can leave all those as defaults, but we need to write to color. And hey presto, there you go. We can write to anything, you can make up Memo's new attributes, and now every particle will have a new attribute, which is this. But in this case, we want to write to color. And there you go. So the new particles are being born are white, and as they age on the trail, they move along this. And we could do the same for scale, as I mentioned. So we could create a ramp and you just do black and white. And for example, maybe we want it, because right now, this is linear from 1 to 0, but maybe we want it to start there and then drop very quickly. And let me convert this now to a chop so I can visualize it more easily. And maybe we just want, we don't need all the channels, but just one channel. So now I can visualize quite easily. I can create a curve and let's make it even out. And let's make that one darker and use it more over here, for example. Or you could just use the chop shapers like pattern. Or do, for example, a cosine and phase shifted a bit. Or you can use the envelopes, not envelope, sorry, trigger, which is also an envelope. Turn off the time slice. I've covered this in a previous tutorial. So that gives you a shape like that. And then you can play with the different aspects of this. This is an envelope, by the way, ADSR. So there's the attack, that's the peak, that's the decay, that's the sustain, that's the release. I covered this in a previous video. So then you can use this to look up for the scale, but because this is a chop, you would use lookup channel. And Let's say you put that there and use again age norm and write to scale. So now this, we're overwriting this bit. We still need this bit. We still need to calculate age norm. Let me get rid of, no, I'll leave that up, just so you have it as a reference. But now the particles are being born tiny. They quickly reach peak size, stay there for a bit, and then they shrink. I'm actually going to get rid of that because I prefer it like this. And I will bypass all of these, but I'll leave them there so you have them for reference. So I think that is pretty much covers the static model. Okay, now let's talk about what we need to do if the model is animated. And before I reanimate the model, if you recall, let's go back to the FBX. I said play mode specify index, and index is 31. So I'm going to put this back onto play mode, but recall what's happening. When the particle wanders outside of the model, it is reset. And that happens here, math inside. In fact, let's call that math inside reset. And now let's call it math outside reset. So if it goes outside, it's reset. But where is it reset to? It's reset to start position. What is start position? Start position is calculated before the feedback, based on whatever the mesh was at that point. So I'm going to put the display on for this one, actually. That one and that one, these can be on. If I can also now turn them off. So let's go back. I'm going to make this locked to timeline. Now I'll make it sequential, so it's just running. And let me visualize it. So what's happening is these particles are wandering around. I'm just going to pause it. Wandering around as soon as it goes outside the mesh, but the mesh is here, but it's being reset back here. So this start position is basically useless. So here's what we can do. And this, I don't think this is the most efficient way. To be honest, the way I would do this whole thing, I would do the whole thing in a single GLSL shader, and I would only calculate a random inside position for the points that are needed. But just for simplicity, what I'm going to do now is I'm going to create these sprinkle and start pause. I'm going to move it down here. Let me pause this. So here's what we need to do. We need to recalculate start pause every frame. We need to resprinkle and recalculate the start pause every frame. So we still need to feed this into here. So note, I'm not saving start position. So here's my model. It comes in. I shrink it a little bit. This was a, let's call this math shrink. So we shrink the model, if you recall. Let me turn that one off and turn this on. Right, this shrinks the model a tiny bit. We don't really need to do that probably, but anyway, we sprinkle points inside. Oh no, that's the null sprinkle mesh. This is the sprinkle. So that's sprinkle. That's what goes into feedback. And then we don't really need this one anymore. I'm going to turn that one off. But I'm going to hook this up straight to this as the second input. And here on the inputs, I'm going to say from the second input, which is this sprinkle, which is happening every frame. See, what goes into the feedback this is no longer red after the first loop. Remember, when you first initialize the feedback, this chain is run, it goes into the feedback, but then we're stuck in here. And we're not reading what's coming in from here again. So instead, I'm going to go straight into this, into the second input. I'm going to say, take the position and rename it to start pause. And then here on the combine, now this start pause is not a start pause that was calculated once before the feedback, but it's a start pause that is being constantly updated, and this sprinkle is happening every frame now. So let me save and run and not visualize that. I forgot to reset, so there's already a start position attribute. I think what's happening is there's already a start position attribute on the particles because I haven't reset yet. And so this is from the previous time I initialized. So let me try resetting. Okay, now. So I had to reset it. I don't know if this is a bug or a usability thing, because all the particles already had a start pause attribute. Here, there were two start pause. There was a start pause attribute, which it already had on the particle itself, and there was a start pause coming in from the second input. But here it was using the one that was already on the particle, which was pre-calculated. So I had to reset. So here this is basically running now. It's leaving a trail because of our trail thing. Let's make that a lot shorter just to visualize easily what's going on. And let's slow down this FPX. So instead of a file, let's use a custom. Let's make that 1. So it's 60 FPS. And let's just load it down. So you can see now we can, let's say, make the trail. So this is the same as before. Particles are being spawned. They're being wobbling around. The collision that they're being checked against is dynamic. This ray, so we can visualize this one. This is a running mesh. This is the mesh that you can see is animated. That's what the collision is being tested against. And if the ray is inside, we use P. If it's not, we use start pause, but start pause this time is being calculated every frame in this chain here. We take the original model that's animated. As you can see, we recalculate normals. We shrink it a little bit. We sprinkle, oh, that's just a null. We sprinkle some points inside it. And yeah, that's what we feed this. Yeah, I was saying this is definitely not very efficient, I don't think, if you had way too many points, because we're sprinkling a million. If let's say you had 1,000,000 points, you're sprinkling 1,000,000 points inside the mesh every frame, only to use maybe some of them. But for a small number of points like this, this is running at 60M on a laptop here. It's working quite fine. So I think that's it. So yeah, have fun.